Greetings, math fans. All right, so today is day 3, and we're going to talk about a little bit more about conditional probability and also a little bit more about independent and dependent probabilities. Okay, so just kind of almost a continuation of day 2. So let's just talk a little bit first here. Conditional probability of event B is in relationship to event A is the probability that event B occurred given that A already occurred. Remember we talked about this? This was dependent variables, right? So something occurred, kind of like yesterday when we talked about what's the probability of picking a queen if we've already picked a king, right? We didn't put the king back, so it changes the probability. As opposed to if we picked a queen, it changes the probability of picking another queen, right? So it's conditional probability that something has already occurred. And so basically the notation for that is, and I'm reading over here, the notation is this here, P probability of BA, that guy right there, okay? So probability of B, there's a line there, A, and that's pronounced the probability of event B given A. So what is the probability of B occurring given that A has occurred already? Okay, so that's not bad. And it says when two events A and B are dependent, which is that's what's going on here, they're dependent on each other, the probability of both occurring is, and so here's your nice little friendly formula which you definitely want to highlight here. Okay, the probability of A and B is the probability that of A times, instead of just the probability of B, it's the probability of B given that A has occurred already. So that this probability right here is kind of changed a little bit right there. Okay, it's not just probability of B, it's probability of B given that A has occurred. Okay, so let's just start out with our first example here. If Billy Bo Bob, that's a good southern name, if Billy Bo Bob asks the prom queen for a date, there's a 60% chance of her saying yes. Okay, but only, again you got to read the whole thing here. If Billy Bo Bob asks the prom queen for a date, there's a 60% chance of her saying yes. He's kind of shy, so there's actually a 40% chance that Billy Bo Bob will actually ask her. But if he did ask her, it's a 60% chance that she'll say yes. Okay? What is the probability that they will go on a date? So what you have here, math fans, is the probability of her saying yes given that he asks. Well, that is given here. That's actually the first statement here. That's the 60%, right? So the probability that of her saying yes given that he is going to ask. Okay, he's got to ask her first. If he doesn't ask her, she's not going to say yes. Okay, so the probability that she's going to say yes given that he does ask her is 0.60. Okay, the probability that he actually asks her, he's shy, but it's a 40% chance he's actually going to ask her. So the probability that he asks her is 0.40. All right, so here's the deal. We're looking for the probability that he asks her and she says yes. Right? That's what I'm asking for, right? It says, what is the probability that they will go on a date? So think logically. The probability that they will go on a date, two things have to happen, right? He has to ask her and she has to say yes. Okay? So, with this nice little probability, let's actually look at that formula that we have here real quickly. Let's move, I'm going to move it down here. This right here, the probability of A and B, which is here it is, the probability of A and B is the probability of A, so the probability that he asks her times the probability of B, so the probability that she says yes given that he asks her. So that's probability of yes, of her saying yes given that he asks her. Okay? And so we have that information now, so it's basically 0.60 times 0.40. So my answer to this problem is 0.24. Okay, does that make sense? So think it's got to be lower than the 60% or the 40% chance, right? That makes sense because first of all, there's only a 40% chance he's even going to ask her. And if he does ask her, it's a 60% chance that she's going to say yes. So that's why you're combining both of these probabilities, because it's a 40% chance that he's going to ask her, 60% chance of saying yes. That's why you multiply the two together. Okay? But again, this part right here, this is pretty significant. This is the equation that you use. Probability that he asks her and yes is the probability that he asks her or times the probability that she says yes, given that he did ask her. Okay? Let's try the next one here. You go to CarMax to buy a used car. I even say, don't buy a new car. Remember, it's a terrible investment. Horrible investment. Buy a used car. Okay, 30% of the cars are stick shift. So we can say the probability of stick shift is 0.30. 40% are convertible. So the probability of convertible is 0.40. It says 15% of the cars have both stick and are convertibles. So the probability of stick and a convertible is 0.15. All right, and what they're asking is you definitely have to have a convertible. So you definitely have to have a convertible. What's the probability that a car will come with a stick shift? Okay, so you're looking for the probability that it comes with a stick shift, given that it's got to be convertible. So given that's a convertible. Okay? So if you look at our original formula here, we can just kind of rewrite this. Let me go back to this original formula here. I am really looking for what's in blue, dark blue here. I'm looking for this, probability of B given A. So I'm just going to rewrite this. That's the probability of B given A is just the probability of A and B divided by probability of A. Okay, we're going to talk about this formula in a little bit, but this is just another way to write it. All right? And by the way, just for common knowledge here, see that A right here? That's that A right there. It's always going to be on the bottom. So whatever it's given, that goes in the bottom in the denominator of the fraction. Okay, so to help you kind of memorize the formula a little bit. Okay, but you can always just divide it out and figure it out as well. All right, so let me rewrite this equation now down here. Okay, so the probability of stick and a convertible is equal to the probability of stick and a convertible divided by probability of a convertible. Okay? So the probability of stick and convertible is 0.15. The probability of just getting a convertible is 0.4. All right, so you divide that out and you get 0.375 or 0.38, really, to round it to the nearest hundredth. Okay, so that is the probability. If you have to have a convertible, the probability of getting a stick shift with all these parameters is 0.38. All right, so let's look at a chart type problem. These are actually, I think, almost a little bit easier. So example 3, I'm given the following data about males and females and whether they are left-handed or right-handed. So basically, if you notice in the chart, you get the gender male or female and male, and you're either right-handed or left-handed. So it's got the totals for like the number of females is 80, the number of males is 50, but the number of right-handed people is 100, and the number of left-handed people is 30. And if you add these up going to the right, it's 60 plus 20 is 80, 40 plus 10 is 50, going down, 60 plus 40 is 100, and 20 plus 30 is 30. And then if I add the 80 plus 50, I get 130. And if I add the 100 plus 30, I get 130 as well. So kind of everything adds up, okay? So here's the deal. A student is selected at random. What is the probability that a student is a female? So remember, probability is success over total outcomes. Okay, and so our success is a female. All right, so the probability of student success is student is a female is our success. And how many females are there? Well, there are 80 of them, because this is right here, 80. So it's 80. Let's see if we can write this out. Probability of a female is 80 over the total. And how many are there? There are 130. Okay, and so you get 0.62. Okay, that's not bad, right? 0.6, pretty easy, pretty easy. Okay, B, it says, what is the probability that a student is left-handed? Okay, well, let me move this down a little bit. Well, how many left-handed students are there? There are 30. So probability of left-handed is 30, because there are 30 left-handed students. And what's the total? Over 130. So you get 0.23. Okay, not bad so far. Let's keep going here. What is the probability that the student is a female, given that the student is right-handed? Okay, so first of all, it's given that the student is right-handed. So the student has to be right-handed, and you want to know the probability that the person is a female. So let's go back to the chart now. So what we're going to do this with a calculation, and then we're going to do it just by looking at the chart. Okay, because I want you guys really to see it both ways here. So the probability that the student is female, given that the student's right-handed. So first of all, you know the student's right-handed. Okay, and so if the student is right-handed, there are 100 students that are right-handed. So what is the probability that that student is female? You know they're right-handed, so there are only 100 students to pick from. So this is basically my total. And my success is, again, being female, so my success is 60. So the probability is 60 over 100. So the probability of that the student is female, given that the student is right-handed, we said is 60 over 100, okay, which is 0.6. Now that's just kind of looking at the chart. Let's say we did it using our probability. So we know probability that it's female and right-handed, that's equal to the probability of female and right-handed divided by the probability, and remember that right-handed goes down here, so right-handed. Okay, so let's go back up here. And by the way, I'm saying probabilities, and I know I'm saying like 30 and 130. You can use the numbers because your denominators are going to be the same, and they'll cancel out. So it doesn't matter if I use the numbers or if I use the probabilities. And by the way, yeah, okay, so let's go up and check it out here. So the probability of a female and right-handed, let's see how many there are. So female and right-handed, there's 60. Everybody agree with that? That's probability of female and right-handed is 60. So let's put 60. And what's the probability that the person is right-handed? Well, out of the total, how many right-handed people are there? There are 100 right-handed people. Right? So you go down here, and there are 100 right-handed people. So we get the same thing. Okay? So kind of trying to show you a little bit, almost logically using the chart and then actually using the formula. Okay? So probability of female and right-handed, you're getting both. It's where it intersects. Female, female, and right-handed. There are 60 of them. And then the probability of just being right-handed, there are 100 of them. Okay? Not bad. All right, the last one, D here. If I knew a student was male, what is the probability that the student was left-handed? So if I knew this, I knew the student was male, when I say the probability of something, given something, that's what it's given. I know the student's male, so it's given the student's male. I want to know the probability that the student was left-handed. And this is the setup. Probability of the student that was left-handed given that they were male. So let's go to the chart first and just kind of see what we have here. Probability that the student was left-handed given that they were male. Okay, so let me erase all this stuff off the chart. Okay, so probability that the student is left-handed. First of all, they're given it's male. So how many males are there? Okay, well, there are 50 males. So what's probably they're left-handed? 10. There's 10 males that are left-handed out of 50. So that's my answer. What? That easy? It's 10 over 50, which is 0.20. Okay, that's not bad, right? Pretty straightforward. Now let's actually use the equation. Okay, so the probability that person's left-handed given that they're male is the probability that they're left-handed and male divided by the probability that they're male. Okay, so let's take a look at the chart. Probability they're left-handed and male. So let me just erase the things I just did here. Probability that they're left-handed and male. So left-handed and male is this guy right here, 10. So it's 10 divided by the probability that they're male, which is 50. Now again, remember how I said we're talking about probabilities here? And I've been just like pointing to numbers and there's no probability. But let's think about it logically. So we said 10 over 50, right? So if I would actually use the probabilities, what's the probability that they are left-handed and male? Well, it's 10, write this 10 here, 10 out of 130. Everybody agree with that? So let me write 10 over 130. That's the probability that that person is left-handed and male. 10 out of the total of 130. Okay? Divided by the probability that they're just male. Well, what's the probability that they're just male? Is 50 over 130. All right, so notice that the 130s really just cancel out and we wind up getting 10 over 150. That's kind of the nice thing about actually having a chart is you don't really have to do that bottom number for the probabilities. You can, but you don't have to because that bottom number is the same, which means it just cancels out. Okay? All right, so let's move on to our last problem here. This is again talking a little bit more about independent and dependent probability. Remember we talked about this yesterday. When two events are independent, then their probability is just probability of A times probability of B. It's pretty easy. And when two events are dependent, this is what we talked about just now. The probability of A and B is probability of A times probability of B, given that A occurred already. And here this guy right here, I just rewrote it, solving for probability of B given A, which is what we did in the last problem. Okay, so once again, just trying to talk a little bit more. It says if probability of A is equal to probability of A given B, if those are the same values, then the events are independent. Because if it's probability of A doesn't matter about B, then that's why these two would be equal, because they don't matter if B happened or if it didn't. If those probabilities are the same, then they're independent. So A does not matter if B occurred or not. Okay? But if they're not equal, so right here, if they're not equal, that means that they are dependent because the probability of A is different than the probability of A that B occurred already. Okay? So it does matter now if B occurred or not. Okay? All right. So let's do this next problem here. It says Doug has a closet full of multicolored clothes. A blue tie, a green tie, a red tie, blue shirt, red shirt, green shirt, orange shirt, blue pants, red pants, and blue shoes. Okay? And I'm finding all kinds of different probabilities. So first of all, there are 11 items here. Let's actually write that down. I think it's just a good thing. 11 items. Okay, and the reason I write 11 items is because we're going to need that for our denominator for probabilities, right? Okay, so it says, what's the probability of just grabbing blue clothes? Well, blue clothes, how many blue clothes are there? If I count the number of blue ties, and blue shirts and blue pants and blue shoes, I've got 1, 2 blue ties, 3 for blue shirts, 4 for blue pants, and 5 for blue shoes. So there's 5 blue clothes out of a total of 11. That's pretty easy. What's probability of picking a tie? 1, 2, 3, 4. There's 4 out of 11. Okay? So what's the probability of picking blue clothes given that I picked a tie? So here's the deal. How many ties are there? There are 4 ties. That's my denominator. Because I know I picked a tie, so that's my total is on the bottom is the 4. And then the success is picking blue clothes out of that. And how many blue ties do I have basically? 2. So my answer is 1/2. It's probably picking blue clothes given that I picked a tie. All right, once again, you could have used, we could have used our nice little friendly formula here. So let's actually just do one problem like that. Do you guys agree picking probability of blue clothes given that you get picked a tie is the probability of blue and a tie divided by the probability of a tie? Okay, so the probability of picking blue and a tie, well, again, there's 11 items, so the probability of picking blue and a tie, there are only 2. There's a blue tie and a blue tie, right? So there's 2 of those, 2 over 11. And what's the probability of picking a tie? Well, aren't there 4 ties? So it's 4 over 11. And what happens to the 11s? They cancel, and you get 2/4, which is 1/2. Okay, so it's a lot easier just like looking at the chart and picking everything off rather than trying to use the formula. But you can use the formula. Okay. All right, let's look at the next one. The probability of picking a tie given that you have blue clothes. Well, again, how many blue clothes are there? We said there's 1, 2, 3, 4, 5 blue clothes. Okay, and how many ties are blue? Okay, well, 1, 2. So the answer is 2/5. What? That's pretty easy. Okay. All right. Probability of picking orange clothes given that it was a shirt. So we got to scroll back up here. Orange clothes given that it was a shirt. Well, again, given it's a shirt, how many shirts are there? 1, 2, 3, 4 shirts. And how many orange ones are there? 1. So what's the probability? 1 over 4. Really easy. Probability that it's a shirt given that it's orange clothes. Well, how many orange clothes are there? Okay, 1. An orange shirt, that's it. So there's only 1 of those given that it's an orange shirt. And what's the probability that it's a shirt? Well, how many shirts are orange? Well, 1. Oh, so the answer is 1. So in other words, 100% chance you're going to get it right. Think of the question. What's the probability that you pick a shirt given that it's orange? I'm telling you it's orange. What other orange clothes do I have? Nothing except for the shirt. So if I tell you it's orange, it's got to be the shirt. Okay? Does that make sense? Okay, let's take a look at the next one here. What's the probability of picking green clothes given that it was pants? So, well, okay, let's look at pants. How many pants do I have? I have, I know it's pants, so there's 2 pants down there. Okay, and how many are green pants? Well, they're none. So it's 0. Which it makes sense again. What's the probability that it's green clothes given it's pants? I'm telling you it's pants. So you look and say, well, how many pants do I have that are green? Oh, I don't have any. Oh, okay, 0. Okay, so the next one, probability that it's pants given it's blue clothes. So how many blue clothes do I have? Well, we already said 1, 2, 3, 4, 5. So there's 5 blue clothes. And how many pants have blue clothes? So once again, I'm telling you it's blue clothes. So it's out of 5. And how many pants have blue clothes? Well, 1. Right? Blue, here it is, like the blue pants. So it is 1/5. Okay? Now this is a little bit different. These are all conditional, right? These are all, something green clothes given something. Now it's a little bit different. What's the probability of picking blue clothes and a tie. So you got to pick both. Well, again, let's look logically. What's probability? You have to have both. What's probability of picking blue clothes and a tie? Well, there's a blue tie and a blue tie. Two blue ties. So the probability of picking blue clothes and a tie, there are two of them out of the whole amount. So out of 11. So it's 2 out of 11. Oops, 2 over 11. Okay? Now, again, we could have done that using probability, right? I could have said probability of blue clothes and a tie is equal to the probability of blue clothes given that there's a tie times the probability of a tie. Right? I just kind of reversed these. You could rewrite it. It doesn't matter. Probability of a tie times blue given there's a tie. Okay. So let's figure that out. What's the probability it's blue given that there's a tie? Okay, well, if it's a tie, that means there's 4 of them, and what's probably that it's blue? There's 2 of them, so it's 2 out of 4. So let's write that. 2 out of 4. And what's the probability it's a tie? How many ties are there? 1, 2, 3, 4 ties out of 11. So 4 11s. And what happens to the 4s? They cancel. Hey, we got 2 over 11. 2 11. It's our district. Perfect. Okay? So which way is it easier? I think it's easier to just to look at the chart and pick it off as opposed to trying to use the formulas. But it's your call. So again, probability of red clothes and pants. Let's go to that. Red clothes and pants. So how many red pants do I have? Let's get rid of some of this stuff here again. Okay. How many red clothes and pants? There's only one. There's only one red pant. So remember, it's kind of the intersection of both of them. It's got to be red pants and it's got to be red and it's got to be pants. There's only one of them. So it's 1 out of 11. 1 over 11. Okay. Now we got or. All right, so that's interesting. What's the probability of picking blue clothes or tie? So in other words, I can pick blue clothes. How many blue clothes are there? So again, going back to here, how many blue clothes are there? Well, we said there are 5. So 5 11ths. Let's write that in here. 5 11ths. And what's the probability of picking a tie? How many ties are there? 1, 2, 3, 4 out of 11. Okay. So remember, this is from the first day of probability. So 4 out of 11. But what's the problem here, math fans? What just happened? Okay, I just counted, we counted blue clothes and we counted ties. But what happened is I counted blue clothes and ties, so I counted these two twice, didn't I? When I counted blue, I counted 1, 2, 3, 4, 5. And when I counted ties, I counted 1, 2, 3, 4. And I counted those, what I just circled in red there, I counted those twice. So what do you have to do? You have to subtract the overlap. So minus 2 over 11. So that gives us 7 over 11. And that's the answer to that, because there was overlap. Okay? So overlap. Got to remember that. That's from day 1, basically. Okay, so another one. Probability of green clothes or pants. So first of all, let's count the number of green. Okay, if I count the number of green, there's a green tie, a green shirt, and that's it. So it's 2 out of 11. Okay, so 2 over 11 plus pants. Probably picking pants, there are 2 pants, a blue and red. So plus 2 over 11. Okay, and the overlap would be green pants. So what I counted twice. And if you look, there are no green pants. You just have blue and red, so there's no overlap here. So the answer to this problem is 4 11ths. There's no overlap. Okay? So that's kind of it, math fans. Just, again, we'll call it conditional probability, something given something that occurred. Okay, and I tried to show you a little bit with a chart and some data, and you can use a formula. You can just use the chart. Either way, but just know what you're doing. All right, that's it, my fans. Have an outstanding day. Adios. Goodbye.